Somewhere, deep in space, a distant star is flooding our universe with photons, little packets of energy that we know as light. It is sending out light of many different energies, which to us look like different colors. These photons speed across space unchanged, until eventually a small number of them encounter a cloud of gas. This cloud of gas is the atmosphere of a distant planet. Trillions of photons encountering trillions of molecules in sort of a cosmic dance. When a photon with just the right energy encounters a molecule with just the right vibrations and rotations of its atoms, the photon is absorbed, and the intensity of those vibrations and rotations increases. Photons that don't find a partner emerge from the other side of the atmosphere untouched. But this light now has the imprint of that planet's atmosphere. The light at particular energies that's favored by particular molecules is now gone, and we have a spectrum of remaining light that is able to speak to us. It's able to tell us exactly where it's been, exactly what molecules were there: methane, carbon dioxide, water vapor. It can also tell us how hot or how cold it was. And this information together tells us the story of that planet. What was there? What was the weather like? If we see certain combinations of these gases, methane, hydrogen sulfide, nitrous oxide, these are signatures of Earth-like life. So perhaps we could even know who is there. That story, written onto that light, now travels across our universe for years and years, until finally these photons smack. They slam into the telescope, the detector of a telescope, like Hubble, or the upcoming James Webb, which are watching our skies looking for celestial stories to read in the light that they receive. See, these telescopes are able to measure how much light is there of each color, of each energy. But there's just one problem. In order to understand this book, we need to understand the language of the molecules that wrote the book. We need to understand which molecules absorb which light. And we need to understand how that changes if the planet was hot or cold. So what do we need to understand this language? We need a book, a key, a cipher that can tell us how to interpret and decode the language of those molecules. Believe it or not, this is happening right now, right here in Boulder, Colorado, the University of Colorado and the Department of Mechanical Engineering. And this project, to understand the language of light, actually started with projects right here on Earth. For the past 6 years, my team at the University of Colorado has been researching how to use lasers to see different environments on Earth. We use them to sense combustion, for example, to help us understand wildfires and how they spread, or how to make engines better. All of the work that we do relies on this very same principle. We send light through the environment, like the fire or the engine. We look at the light that returns. Where there are certain molecules present, they absorb different colors, and that tells us what was in the fire and how it was evolving. But to understand that light, we too need a map, a key, to know what was there and what the temperature was. So in our lab, we started to build furnaces and high-pressure chambers so that we can have controlled conditions in the lab that are like the conditions in the engines in the fires. We send the light through, and when it comes back, we see certain patterns of light based on what we put in the chamber. Each of these patterns is like a page in a book. This is what methane looks like. This is what CO2 looks like. And we do this over and over again, and that's how we build the cipher, this Rosetta Stone for the language of the molecules. The lasers that we use in these chambers are very unique as well. They're Nobel Prize-winning frequency comb lasers from right here at Boulder, developed at CU and at NIST. These lasers emit hundreds of thousands of colors of light, all at the same time, and this gives us vast information about the relationship of light and molecules. So vast, in fact, that we needed help to cope with it all. We reached out to some colleagues at Jet Propulsion Laboratory in Pasadena to help us interpret this data. And when they arrived out to Boulder to help us, what took their attention was these chambers that we had built, the lasers that we were using. And this, what they said, is what we need to understand the signals that are coming from the distant planets that we're seeing with Hubble. So now, we're using these chambers, we're using our lasers right here in Boulder to build the maps, to understand the light that has passed through the atmospheres of these distant planets. And so someday, in the not-so-distant future, we will look out to the light that's reaching us from these distant, far reaches of the universe, and we'll read their stories, coded in the light. And we're going to watch. We're going to watch for a very certain, specific story, a story that looks like the story our own atmosphere would put on the sun's light as it passes by. And we'll watch for a story that says, we're here, and the weather is beautiful. Thank you.